try using some of these suggestions to help you with some of the questions that you had on the packets. For K here in the first packet, here's a common trick that we often use. Rather than relying on a quotient rule, what we'll often do is rewrite a function that looks like this with just a single exponent. And if you recall, the power that's down here in the denominator of this fraction can actually be written as a negative exponent. And if we apply the power rule, t to the negative fifth power, then when we bring the negative 5 down and reduce the exponent by 1, we've got an expression that looks like this. Now, I wouldn't leave this answer in this form because the original problem started as a fraction. We should probably rewrite our final answer as a fraction. So this t to the negative sixth power becomes t to the positive sixth power as soon as we move it back down to the bottom of the denominator, bottom of the fraction. And I think that would be a fair response for the derivative in K. Part M is done in a similar fashion. So I would rewrite this equation first as, well, we'll leave the z squared alone. And then I'm going to treat this 1/2 as a coefficient. And then this z, which technically is z to the first power in the denominator of a fraction. So it's kind of like 1/2 times 1 over z. So I'm going to treat this as 1/2 times z to the negative first power. And now we can apply the derivative rule, especially the power rules, to both of these terms, much like we did in part K. I'll come back to these word problems in a minute. Let's talk about BC on the second packet. You know, in the real world, you certainly could distribute this x squared into the polynomial and then treat it just like one of the examples from the first packet. But I chose these two problems because it gives you a chance to practice with the product rule for derivatives. So if f of x is made up of the product of two other functions, then we should use the product rule for finding their derivatives. And originally, when I made the video to introduce the product rule, we said to write a mini function for the first one and a mini function for the second one. So I'm going to call the first function x squared, and then the second function is x cubed plus 5. Now the derivative of the first function is 2x, and the derivative of the second function is 3x squared. The plus 5 turned to a 0 with its derivative. When we cross multiply, these cross products must be added together for the product rule. And so we would say something like this, that f prime of x is equal to 2x times x cubed plus 5. So I started with this cross product first. And then to that I will add x squared times 3x squared. That was the second round of cross products. I like going in that order because that'll be the same for our quotient rule later. And then from here I would simplify. On the test next week, I won't ask you to simplify, just so that we can save a little bit of time, but since this is homework and you're working on it for an extended amount of time, I would ask you to simplify. And so, distribute this 2x into this group, multiply these two terms together, and then combine any like terms that you encounter in that process. For part C, I would approach it the exact same way, and I would treat this mini function as f and this one as g, and I would set up the functions off to the side and do the cross multiplication to simplify them. And again, I'll come back to the word problems in just a minute. For part J of our third packet, I would probably rewrite this function, or at least think about it in this other form. Instead of the square root of e to the x power plus 1, let's treat this as e to the x power plus 1 raised to the 1/2 power. If you recall, any radical can be written as a fractional exponent, and so the square root would be a 1/2 power. A cube root is a 1/3 power, and so on. So if we've got the power of 1/2, well, now we've got an inner function, which is e to the x plus 1, And then the outer function, of course, would be something to the power of x. And we could follow our chain rule from there. So chain rule would be, let's see, I should have enough room here. Taking the derivative of the outer function first, so that would be 1/2 times something to the negative 1/2 power. That brings the exponent down and then reduces that exponent by 1. The something in this case is untouched for the time being, but then after we've established the derivative of the outer function, we immediately multiply by the derivative of the inner function. And if I'm focusing on this inner function only, its derivative is e to the x power. This plus 1's derivative is just 0, so that goes away. And here again on the test next week, this would probably be okay as a final answer, but since this is a homework assignment that you've got extra time to work on, we can simplify it. The 1/2 essentially creates this fraction, and e to the x power plus 1, that stays in the top. E to the x power plus 1 stays in the top, while the 2 from the 1/2 is in the bottom. And rather than writing this as a power of 1/2, since this original problem started with a radical sign, I would probably rewrite this one as a radical as well. So we'll say the square root of e to the x power plus 1. And then we also, oops, I forgot that's a negative 1/2 power. It's a negative 1/2 power. So the negative sign means that this power gets pushed to the denominator. There we go. That's better. So we've got 1/2 still, and with that 2 now sits this negative 1/2 power exponent. And then the e to the x, well, that's a positive exponent, so we'll move that up to the top. And 1 times e to the x is just 1, so I might report the derivative like this. So here's f prime of x. For a question like part B, we need to find the derivative first and then take that derivative and divide it by the original function. That's what's going to produce a relative rate of change. And anytime that we see a relative rate of change, this term relative is a mathematical phrase that means percentage. So all of these relative rates of change, even in the word problems from earlier in the packet, they just mean to produce a percentage change at a particular point. So in this example, we've got a coefficient that's multiplying by e to the negative 7t power, and that's really just one of our rules from the derivative set that we memorized at the beginning, e to the kt power, so we know that its derivative. So I'm going to say that f prime is equal to 30. I'm going to just push that out to the front, and then multiply that by the derivative here, which would be negative 7 e to the negative 7t power. And to clean it up, because I can, negative 210 e to the negative 7t power. That's our derivative function. So when we report the relative rate of change function, that would mean to take this derivative, negative 210 e to the negative 7t power, and divide it by the original function, 30 e to the negative 7t power. And this produces a pretty interesting result here, because e to the negative 7t power does cancel out, or factors to 0, and the fraction negative 210 divided by 30 will simplify to equal negative 7. So our relative rate of change is negative 7. And we'll revisit this notion of relative rates of change when we talk about our related rates formula in Unit 4. But for right now, if we just call this relative rate of change negative 7, that would be just fine. Doesn't always work out this way. It's just interesting that the original function and its derivative contain pretty similar components. And for problems like A and C, I wouldn't be surprised if you see a result that's significantly different. Now, with the word problems that I've selected for this packet, the questions really do depend upon, or I should say your responses really do depend upon how the question is worded and what the units are within each problem. So rather than going through all of these in this particular video, I'll just talk more broadly in terms of units and how they are they're to be described with functions and derivatives. So in a problem like number 3, we're saying that n, which is the number of acres of harvested land, is the result of some function that's based on time. I use this double function notation just as a reminder in case you see this in other textbooks. But really the equation could be written as, n equals 120 times the square root of t, or it could be f of t equals 120 times the square root of t. They both mean the same thing. And we're just kind of expressing that the number of acres is based on some equation, some function that depends on time. So when we ask you to evaluate f of 9, that literally means to substitute the number 9 in place of t, and that math's not too hard. 120 times the square root of 9, which is 3. So 120 times 3 is 360. Now units are really important here, so 360 what? Well, f of t does represent n, and n was the number of acres. So with f of 9, 9 being 9 years, 9 years after, or 9 years since farming has begun in a particular region, 360 acres are being harvested. With derivatives, we'll do the same thing. We'll determine what our derivative is, and I'll let you figure out the result for that numerical component. But when it comes to time, or it comes to our unit, we've got to include both our vertical axis and our horizontal axis in our units. So we've got the number of acres on the y-axis. That's what this n value is representing, the result of our function. So we've got acres along the y-axis and time in years along our x-axis. So when we talk about a derivative being the slope of a tangent line, we would say that the y-axis unit divided by our x-axis unit would be appropriate. And whatever answer you got for f prime of 9, so this derivative evaluated at 9, we would take that number and say that it's that many acres per year that the function is changing. Now this was some generic picture that I sketched over here. If I'm not mistaken though, because of the radical sign, the graph is going to look something like this. And so your answer for part B should be a positive value because there is a positive slope to this curve. And while the data point right here would be 9, 360, because after 9 years the number of acres harvested are 360, the slope at this point is going to be much less than that, but it is still a positive number because we are still seeing a growth in the number of acres per year that are being harvested. When we divide your answer for B by the answer for A, then this result will represent some sort of percentage or relative change. For number 4 in this first packet, again, I don't expect you to be an expert on these functions, but I hope that by reading for context clues and interpreting the equation itself, you'd have a pretty good idea of what we can do from here. I'll just remind you that P and Q are the axes for this particular problem. And since P is the calculated result, I'll place that along the y-axis. And Q, since that's the independent variable, I'll place that along the x-axis. When we look for a p-intercept, much like we would when we're looking for a y-intercept, we would set q equal to 0. Okay, so if you're looking for a p-intercept, set q equal to 0. And when you're looking for a q-intercept, then set p equal to 0. And so in the equation, well, we're looking for the p-intercept, which we don't know what that is. So we'll set y equal to 0. We'll say 50 minus 0.03 times 0 squared is equal to p. And then for the q-intercept, we'll set p equal to 0. And in either case, we'll solve for the variable. So this p-value is easy to solve for. We'll just execute the expression on the right-hand side. This q variable is a little bit harder to solve for, but you can still do simple algebra to isolate that q value. Now for part B and C, I think you can probably find the function result at 20 and the derivative at 20 without too much trouble. You're just evaluating this function and finding its derivative and evaluating that derivative. But I'll just remind you, especially if you haven't had econ in a while, P and Q are price and quantity in a demand function. So when we talk about supply and demand. So this formula is really saying that price depends on some function that is calculated against the quantity of material that's being demanded. So since P is price and price is equal to that function, when we evaluate that function, our unit will be price, which in our case is going to be dollars, and the F prime would be a combination of our price unit, divided by our quantity unit, which we don't really have a unit for that. This would be like the number of objects. So as far as the unit goes for part C, we would say that the unit ends up being some price per unit. So how does the price change for each unit that's being demanded? With part 6, part B, how fast does this model predict Hungary's population will be decreasing? Well, this is just another opportunity for us to utilize our derivative rule. Because when we talk about rates, how fast something is changing, and especially if we see our unit, people per year, people would be our y-axis unit, and year is our x-axis unit. Well, that's exactly what this population is telling us. And if I'm not mistaken, this particular graph would have this type of shape to it. And if I need to know what's the rate in people per year in the year 2020, well, I would just find where 2020 is on this particular graph. Now, 2020 is 11 years after 2009, so I'm going to use an x value of 11, or t value, I should say, a t value of 11, because that's 11 years after 2019, or 2009. And I don't want the population, I don't want to evaluate 11 in this equation, not this one that's provided to us. I want to evaluate 11 in the derivative equation. So once you find P prime, which you can use your exponential rule, because we've got a base, a b value of 0.997t, and an exponent of t here. So if you look at your derivative rules, you can find the derivative of b to the x power and use that here. But once you establish that equation, that's what I would use to evaluate part B. Now for part A in number 7, we're told that a tree that originally contained 185 micrograms of carbon is now 500 years old. And we'd like to know what rate is the carbon decaying. Well, remember, rate is a derivative, so we better work with the derivative of A of t. We're told that A sub 0, this parameter, if you will, is our initial amount of carbon. So we're going to say that our A value in this problem is 185, and we've got e to the negative 0.000121 t. So the first thing we have to do is find A prime of t. This is the formula that would allow us to find our rates. And then once I have the derivative function, then I'll evaluate A prime at 500. So again, this first function tells us how many micrograms remain. So we have micrograms as our unit, but this function tells us the rate at which the item is decaying, and so this would be micrograms per year, our rate. As I reread part B, I realize that part B really isn't a calculus question. It's a question of really college algebra, your ability to solve an exponential problem. And so we covered this in Unit 3 of college algebra last year, but in case you forgot, first thing we need to do is determine our growth rate per year, or in this case a decay rate per year. We often call this growth factor, I should say, not growth rate, but growth factor. A negative growth factor means decay. So we'll find our growth factor first, and then we'll answer the question. So to find our growth factor, we'll start by using components that we already know. In 1988, which is sometime after this Shroud of Turin was made, there was 91% of the material left, and we assume that when it was made it had 100% of the material. So I'm following this rule here. So the amount that was left after a certain amount of time is 91%. The amount that it started with is 100%. And we've got e to the negative 0.000121 t power. And so all we have to do now is solve for t. I had forgotten that this problem actually did give us the growth rate, so we don't really have to determine our growth rate or growth factor. We can really just answer this question from here. We just have to do the math necessary to solve for t. So we'll move the 100 to the left side of the equation by dividing, and 91 divided by 100 is 0.91. And if you recall, an exponential with a base of e can be rewritten as a logarithm. We call that a natural logarithm when the base is e. And when we rewrite the logarithm using the old loop rule, we'd have a logarithm with a base of e evaluated at 0.91, and that's going to equal the exponent in our exponential, 0.000121t. Now, I don't really need that letter e for the base of the logarithm, but whatever the logarithm evaluated at 0.91 is, we'll take that number and divide it by 0.000121, and that will establish our t value, the amount of time that's passed in order for the carbon-14 to reduce from 100% down to 91%. So I know this video is getting a little bit lengthy, but I'll go ahead and try to comment on the last few problems. And you can skip around as needed and try the remaining problems on your own. So I think with part B here in number 4, this is in the second packet, the first thing that we've got to recognize is that C and K are going to be some constant or some numerical value. So if we were to find the derivative of P with respect to R, well, we're going to use our quotient rule, and our quotient rule says to take the low function, K plus R, and multiply it by the derivative of the upper function. Now, C is a constant, so it represents a number. The derivative of a constant times a variable, R is the variable, would be just that constant. This is just like the derivative of mx rule, some constant times the variable x. So that's our low function times the derivative of the high function, minus the high function, CR, times the derivative of the low function. Well, again, here's a number plus a variable, so a constant plus a variable. Well, the derivative of a constant is just 0. The derivative of a plain number is 0, plus the derivative of a single variable, just like the ddx of x, we would say the derivative here is 1. And that numerator is divided by k plus r squared. On the test, that would be good as an answer, but for this homework, since you've got the time, I think it would be good to distribute and combine like terms. But once you have that derivative, Part B is really asking about the meaning of that derivative. Well, let's remind ourselves that P stands for population. So population is going to be, number of, say, people, if we're talking about a population of people. This could be a population of fruit flies for all we care, but it's a population. So let's just say number of people for this particular case. And This is not a growth curve based on time, but it's based on the amount of resources that we have. And so let's say the resource that we're using is, I don't know, gallons of water. So the number of people that are supported in this population is dependent upon the amount of water that's available. And so when we talk about the derivative, that would be the amount of people that can be supported based on that particular resource. So in this example, it'd be people per gallon of water. Now, it seems kind of strange at first to talk this way, but certainly I think you can predict what would happen if, say, we were to reduce the amount of water that's available to a particular population. As the amount of that resource declines, as it lowers, then the number of people that can be supported will lower as well. And if a population is used to, say, 10,000 gallons of water, and we reduce that to 9,000, well, that's not much of a change, and the change in the population will be relatively small. But if we had a large change in the amount of available resource, let's say we only give 500 gallons of water to support the population, well, then the number of people that are supported by that particular resource is going to be much less, and it's probably going to be dropping at a faster rate. So while you describe Part B, I don't think you have to use people and gallons of water as your resource. That's not necessary. I just chose that as a singular example. Perhaps, develop a sentence or two that describes what would happen to the rate of population growth based on the amount of resources that are available, because that's what this particular derivative is describing. Okay, in Part 5, we've got a pretty interesting problem. This is something that engineers tend to gravitate towards. And we're going to try to address this problem to help them out a little bit. Now, the equation that was provided here doesn't actually model the scenario that I'm about to draw, but this is the one that seems to make the most sense to students. Inside the engine of a car or a motorcycle or something like that, we have these cylinders. And inside of a cylinder, there's what we call a piston on the inside. So a piston is basically another cylinder that sits inside of a cylinder. And this piston moves up and down. So it's going to move up and down as the engine fires and creates power for us to move the vehicle. And so what the problem here is asking, when the piston is at the bottom of its stroke, the cylinder in which it operates is only this tall. And it's only taking up part of the cylinder bore. As time passes and this piston moves upward, then the amount of space that piston occupies is going to be a little bit larger. So that piston is going to move up to here, or eventually up to this point when it's at the top dead center of that cylinder's bore. And so now the cylinder ends up being this tall. The amount of occupied space within that cylinder is this height. Well, the height or the position of this piston is based on a function relative to time. So x of t. And that's what part 1 was, well, not part 1, but that's what the original part of the problem was describing. Here is the position of that piston over time. When we calculate the derivative of that piston, we're calculating the rate, or how fast that piston is moving. And so inside of a car's engine, there's a cam or a bar that these pistons are mounted to, and that makes this piston move very, very fast while it's traveling far away from the cylinder head, the top of the cylinder. But as it gets closer to the top here, it slows down. Its speed is actually different. And the derivative function ends up giving us our speed, essentially, in this case, centimeters per second, whatever that formula was. Now, for the question at hand, we need to find the volume of this cylinder. all that x measures is the horizontal distance, or vertical distance, depending on your orientation. It measures the height of the cylinder that's being taken up by the piston. What we need to know is the volume, and the volume requires this cross-sectional area to be multiplied by height. So you may have seen a generic form of a volume formula before, where volume is equal to the area of the base times height. That's why we would use a capital B here, where capital B means area of the base. So whether this is a cylinder or a prism or any other right shape, if we find the area of the base and multiply it by the height, that gives us our volume. So since the cross-sectional area of this particular cylinder is a circle, we're saying that the area of the base is pi r squared, and the height of the cylinder is that formula x of t. Well, the variable in this problem is t, it's not r, and we are told that r is equal to 4. So pi times 4 squared must multiply by x of t, which was 8t over t plus 1. As we simplify this, we can now determine the volume formula for this particular problem. Now, if the volume formula tells us how much space, essentially centimeters cubed, how much space is taken up by this piston, or this section down here, how much space is taken up, then v prime of t will tell us how that space is changing. What's the rate at which that space is changing? If the piston is moving upward and occupying more space in the cylinder, then we're going to see the volume formula change with time, and actually increases a little bit more slowly as it reaches the top of its stroke. And for the last couple questions, for part 3 and packet 3, this formula tells us the revenue. Now, revenue in terms of economy is the amount of money that's brought in dollars, and Q is the number of goods, so number of items, or number of units, if you will, that are being sold or purchased. And so marginal revenue just means derivative. So the marginal revenue is how much does the revenue change when we are producing, in this case, 10 items for sale. Is the revenue going up? Is the revenue going down? And based on this marginal or derivative cost of the revenue, then the business owner or manager can decide to either produce more or less goods in order to meet market demand. So for number 3, just simply determine the derivative r prime and use r prime at 10 to answer part 3. For number 4, hopefully you can attack this one now. Let's treat this distance formula as t cubed plus 1 to the 1/2 power, and then you can find d prime, or in this case f prime, depending on how you note it. You can find d prime with the same techniques that we established in the second packet. And therefore, relative rate of change will be the quotient, where we put f prime of 10 divided by f of 10. And you'll have this answer, you've got this answer, divide the two, and that's your relative rate of change. And again, keep in mind that that relative rate of change will be some number that represents a percent. I think question number 5 is a good one, but I'm not really sure that we need a whole lot of calculus to interpret this. What we're being told is that the amount of wages that you earn is dependent upon additional education you might go after. And so just to use a nice number, $10 per hour, if you're earning $10 per hour and you decide not to go for any extra education, say you don't go to college beyond graduating this year, or after you're at your job, if you decide just to maintain your current education status. You don't go back for additional training or anything like that. Well, your wages are going to increase over time. Now, general inflation indicates that wages tend to grow at 3.5% per year. That's not a guarantee, but that's a trend, an assumption that's being made currently, that on average, people in a professional or in a professional career tend to see a growth of about 3% per year in their income. Now, with more education, we tend to see a larger growth in that per year. And I'm stumbling just a little bit because I'm rethinking how this equation was written, and perhaps we could have done so a little bit better. And I think what might help this make a little bit more sense is if I change this second t value, because really there are two different units of time that are being represented here. I'm going to change the second t value to x, where x, let's see, time t and time x. X would be the amount of time that you spend at your job. So x is the amount of time that you work or that you're at your job in years, and time t is the amount of extra education you might obtain. So if we were to answer part A, how much on average would you earn per hour with 4 additional years of education? Well, that would be an example of this wage function where t is equal to 4. So let's maybe write it this way. Wage based on 0. So 4 extra years of education, but no extra time on the job. So we'll call that 0. And 1.14 to the 4th power would multiply by 10, because e to the 0.35 times 0, well, that's e to the power of 0. E to the power of 0 is 1. 10 times 1 is 10. And this result, when using a calculator, comes out to be 16.89. So without the 4 years of education, say a college degree, you'd be making $10 an hour. But with a college degree, with the 4 years of education, you're making about $16 per hour. Almost $17 an hour. Now, what would happen if you didn't spend any extra time in school, 0 years of school, but 20 years of experience on the job? That's 1.14 to the power of 0 times 10 times e to the 0.35 times 20. So certainly you would see a raise in income if you spent 20 years at a job or 20 years in a career. But how would this number compare to this one? What if you did go to school for 4 years initially and then still experienced your 3.5% growth over 20 years' time? How much difference in your hourly wages would there be then? So I apologize for not being very clear on the set of instructions there. I think I will rewrite this for the next packet. But with these hints here, I think you'll be able to now answer the remaining questions, and hopefully they make a little bit more sense. I know this video was quite lengthy, but hopefully you find it helpful, and if you want to share any of it with anyone else that you speak to, that would be perfectly fine. Thanks for watching.